let us move on to the final 3 questions that we want to discuss. The first question is, are you ready for the new normal? In this question, we'll be talking about normal distributions, a distribution that comes up very often, and we want to talk about why this arises in practice and why this is something that is useful. If we take a look at some data that I generate, and I can generate this data from NumPy, you can see it's kind of a bell-shaped curve. And it's kind of a bell-shaped curve, we might just intuitively say normal distribution. Not a very good thing for us to jump the gun on, because maybe it is, maybe it isn't, maybe it just happens to look like a normal distribution, but it really isn't. But largely, one of the things we can think is that if it really were the case that this were a normal distribution, who cares? Why does anybody care about things like normal distributions and Poisson distributions and Bernoulli distributions? What is the point? Well, if we take a look at this, we can see why somebody might care. Here, we're generating data, and we're generating data, and we're generating concrete data, actual values of data using NumPy. And we might say, I know for certain that there's a certain probability associated where these data points come from, and use that probability in order for you to give me that data set. One interesting thing about this here is this code here using rng.normal is computing actual concrete data. You can see some of the data elements here, and I can compute something like the mean or the variance. Now, you might say, you know what, if I'm using SciPy, I might care about what a normal distribution is. SciPy.stats has a norm. There's something really interesting shows up when you use SciPy.stats.norm. It doesn't give you actual data points. It's not like NumPy random.normal, which is about, pick an actual data point from a distribution given a particular probability. This here seems to represent some sort of abstract notion of what a normal distribution is. And I can ask that abstract notion of what a normal distribution is to pick certain values from it. But here's where we're going to start to see something very interesting. This thing is not actual values. It's not, somebody went and they picked some values and there's 5,000 of them and it gives me, what those values are and compute the mean and the variance. This is an abstract notion of what that distribution is, a theoretical notion of that distribution, but I can compute statistics like the mean and the variance without needing actual values. That's kind of bizarre. But it might ring a bell because you might have seen tricks like that before whenever you did something symbolically. Here I have SymPy.stats, and in SymPy.stats I can create a normal distribution. And this definitely does not represent anything concrete. It's SymPy. It's representing symbolic mathematics. And I can look at these values and I can say, what is x's? Well, x's is x's, or x is 0 is x's. I can say, what's x is 0 plus x is 1? It doesn't compute anything because this is symbolic, so it's just x is 0 plus x is 1. But I can ask, what is the mean, the expectation of this? And this doesn't exist concretely, but it can tell me what the mean is. I can ask it what the variance is. This doesn't exist concretely, but it can tell me what the variance is. I can ask it what the expectation of x's plus x is 0 and x is 1 are. And neither of those exist concretely, but it can tell me what the mean and variance are of these. Fundamentally, why do we care about these theoretical distributions? Well, the theoretical distributions give us some very powerful tools for describing and communicating things about our data sets. They give us a common frame of reference. If I say normal distribution, there are certain implications that come along with that. Namely, it's symmetrical. Whatever we see on the left lobe and whatever we see on the right lobe is the same. It's got a skew of 0. It also means that I can concisely and precisely describe what's happening in that distribution in just a few scalar values. Here, one of the things that you can notice when I am computing the mean and the variance for these symbolic distributions is the mean of my normal distribution is whatever this first parameter was, and the variance of this distribution is whatever, let's raise this up, and the variance is the square of whatever this second value is. What we can say is something like a normal distribution, if we actually had values that were exactly matching up to a normal distribution in the real world, we could say, instead of going through all of those mechanics and worrying about the skew and the kurtosis and the PDF and whatnot, I only need 2 values to uniquely describe every single thing that's happening in that distribution. I just need the mean and I just need the variance, and that uniquely describes this data set. And it gives me a comparative frame of reference, because if I had two data sets that I could both assert were from a normal distribution, I can compare them to each other. I can compare them not by comparing the individual values, of which there may be many, but I can say, just look at the means and just look at the variance, because that's enough to uniquely describe this. The other reason why we care about theoretical distributions is they can sometimes give us some structural or even causative hint. Here's the deal with the normal distribution and why it comes up so much. If we were to take a look at two dice, we could actually use NumPy to physically roll two dice. Physically select two values from 0 to 6 and select 1,000 of them, and select another 1,000 of them. And if we were to do that, and we were to sum them up, roll two dice and figure out what the sum is, and we were to graph the histogram of that, we're going to see something interesting. It seems to be developing a particular shape. And as we increase the number of dice that we roll, the clarity of the shape that develops will increase. It's going to continue to develop something that looks very similar to a normal shape. If we were to symbolically represent two dice, not really roll them, but symbolically represent them, what we could do is we could sum them and ask what the expectation is and what the variance is. And one of the things that we see in practice, this is what's called the central limit theorem, is anytime we have distributions that are, or anytime that we have something that we're sampling, and that thing is independent of each other, and it has a finite mean and a finite variance, if we repeatedly sum that thing up, and we take that to infinity, we get a normal distribution. Normal distributions show up all the time in practice, because they show up anytime you have lots of independent events and you're summing those up. Like you're not rolling two dice, some number of times. You're rolling an infinite number of dice, an infinite number of times. You'll see that it'll start to develop a normal distribution. Normal distributions are very useful because normal distributions also have some very nice properties. Namely, here we have a normal distribution centered around 0 with a particular standard deviation, because this log in the scale, this standard deviation and this mean are all we need to describe this distribution. If I shift every value up 1, I can describe exactly what that does to this distribution. It's basically the equivalent of just changing this to 1. If I multiply every value by 2, then I can tell you exactly what that does to distribution. It's equivalent to changing this scale parameter. And if I were to take this distribution and I were to add to it another normal distribution, I am guaranteed to get as the result a normal distribution. Combinations of normal distributions are normal distributions. If I were to look at things like the mean, the median, the variance, or the skew and the kurtosis, you can see by virtue of this being a normal distribution, there is no skew, there is no kurtosis. Of course, there's a little bit of rounding here. And I can see certain properties around how I might change this data set, move the mean up, or how I might change this data set multiplicity and how that changes the scale, and that relationship with the mean and the variance. And so you can see I have quite a bit of descriptive and comparative ability when I talk about a normal distribution. It is the case that if I were to talk about a normal distribution with a mu and a sigma, with a mean and a standard deviation, I have a closed form formulation for what these summary statistics actually look like. In other words, here is my distribution with a mu and a sigma. If I ask for the expected value of this, the mean of this, it tells me, oh, it's mu. If I ask for the variance of this, it tells me, oh, it's sigma squared. If I ask for the skew, it tells me symbolically, without actually computing any real values, it's this really ugly thing. If I ask for the kurtosis, it tells me symbolically, it's this really ugly thing. But if I ask SymPy to simplify these, you can see the skew is always 0 for a normal distribution. And I haven't even collected real values. This is the power of these theoretical distributions. They give us a clean mathematical universe in which we can talk about our summary statistics and our descriptive statistics without actually needing individualized real data points. And so what you can think, as part of our statistical process, one of the things we might do is take the real data that we observe, figure out if it matches to a theoretical distribution, and if it does, talk about things in terms of that theoretical distribution, because we now have a nice common frame of reference that obeys certain common properties, that is a closed form, very tight formulation for how we describe that data set, and we can, in closed form, directly describe all of these summary statistics that give us the shape without actually having to look at the underlying values. And we can even do things like compute the PDF in terms of X, and you can see here it can give us what the PDF is, and this is the formulation for what the probability of any individual value in a normal distribution might look like. You might wonder why in the statistics module, in the random module in the Python standard library, they use mu and sigma for the two parameters, but in NumPy and SciPy, they use lock and scale. As we said, one of the interesting things about this normal distribution is this lock parameter, this mean parameter, is just where this graph is centered. This scale is just what that standard deviation is. So if I move this thing over to 10, it just moves where the distribution is centered over to 10. You can see, oh, this is centered around 10. And if I increase this scale parameter, it just increases the width. It increases what that standard deviation, what that variance will be. Oh, this thing is now much wider than it was before. Very interesting and very useful way for us to describe in a common frame of reference what's happening with real-world data if we can relate it to a theoretical distribution like the normal distribution. And finally, I want to show you one thing that I mentioned before. I talked about the central limit theorem. Here we have a non-fair die. Here we have a die. It's got 6 sides on it, but if we roll this die 10,000 times, we will clearly see that the probability of getting a 1 or a 2 or a 3 is different than the probability of getting a 4, which is different than the probability of getting a 5 or 6. This is a loaded die. But if we take this loaded die and we take 8 of them and we roll them together and we sum them up, we start to get a normal distribution. Sums of independent, what they call random variables or independent distributions with finite mean and variance, will sum up in the limit to a normal distribution. This is why it comes up so much in practice. Moving on to our next and second to last question,